Hello and welcome to this explainer. I am absolutely thrilled to guide you through today's topic because we're going to tackle something that is literally the bedrock of modern machine learning. We're going to demystify complex data structures and explore the actual anatomy of data itself by looking at matrix decompositions. If you've ever found yourself wondering how on earth an algorithm makes sense of chaotic, massive sets of information, well, you are in exactly the right place.
Okay, let's dive into this. Picture a spreadsheet so vast it has millions of rows and millions of columns. Just a massive, incomprehensible grid of numbers. To us humans, it's just pure noise, right? But how does a computer look at a million data points and instantly find the hidden pattern? How does it know exactly which movie to recommend to you on a Friday night? Or how to compress a massive image without losing the important details? The secret doesn't lie in looking at the whole giant grid at once. It's actually all about breaking it apart.
To get a handle on how this works, let's use a super simple metaphor. Think back to elementary math. When you see a number like 21, you instantly know it can be factored into its prime building blocks, right? 7 times 3. Matrix decomposition does the exact same thing, but for data. Instead of factoring a single number, we're taking a giant matrix and factoring it into simpler, canonical matrix forms. We're literally breaking the big block of data down into its fundamental mathematical prime numbers so we can actually understand what's going on inside of it.
Here's our roadmap for the journey. We'll kick things off with a matrix factorization analogy, move into characteristic numbers and determinants, and then see how we extract meaning using eigendecomposition. After that, we'll introduce the universal tool, SVD, and finally, decode some actual movie ratings data.
Step 1. The matrix factorization analogy.
So keep in mind throughout this explainer that we're really just trying to build geometric intuition here. We're not going to sit around and memorize boring equations. We want to visualize what the data is actually doing. The whole idea is perfectly summed up in a quote from our source material. We decompose messy, complicated matrices into canonical forms. Why? Because those smaller factor matrices are interpretable. They represent fundamental movements like rotations or scaling. By tearing a giant data matrix down into these neat little interpretable pieces, we can finally extract the real hidden structure of the data.
Step 2. Characteristic numbers and determinants.
Now, before we go ripping a whole matrix apart, we usually need to summarize its properties. And one of the absolutely most important characteristic numbers for a square matrix is called the determinant. Now, sure, you could think of the determinant purely algebraically, just doing the math based on a set of rules. But geometrically, it's so much more fascinating. The determinant is a function that maps a square matrix onto a single real number, and that number actually measures signed volume and orientation. It literally tells us how much the matrix stretches or squishes the space it's transforming. It's a foundational characteristic number that summarizes the matrix's entire behavior in just one single value.
And this brilliantly illustrates the concept. Imagine a 3D shape formed by the 3 vector columns of a matrix. The determinant of that matrix isn't just some random number. Its absolute value is the literal physical volume of that 3D solid, which, fun fact, is called a parallelepiped. If the determinant is 0, well, the volume is 0. That means your 3D space just got completely squashed flat into a 2D plane or even a line. You've completely lost a dimension. So this one characteristic number gives us an instant summary of what the matrix is doing spatially.
Moving on to step 3. Extracting meaning with eigendecomposition.
Okay, stepping up from just a single summary number, how do we identify the structural core of the matrix itself? Well, eigendecomposition lets us represent a linear mapping using a diagonal transformation matrix. It goes in and finds specific directions in the data. We call these eigenvectors that absolutely refuse to get knocked off their line when the matrix acts on them. They just stretch or compress. The amount they stretch, that's their eigenvalue, which is another huge characteristic number that summarizes the matrix. By shifting our perspective to align with these eigenvectors, we untangle messy data into perfectly independent orthogonal features. But yeah, there is a catch here. Eigendecomposition generally demands a perfectly square matrix. And I don't know about you, but in the real world, my data is almost never perfectly square.
Which leads us perfectly to step 4, the universal tool, SVD. Enter SVD, or Singular Value Decomposition. In the realms of machine learning and data science, this thing is an absolute powerhouse. The incredibly cool thing about SVD, which, by the way, has literally been called the fundamental theorem of linear algebra, is that it is universally applicable. SVD is a decomposition that works on all matrices, rectangular matrices, tall ones, wide ones, data sets missing values. It just doesn't matter.
It will step in and factorize any matrix into canonical forms, quantifying exactly how the geometry of the data changes from one space to the next.
Let's break down how this works logically into a step-by-step geometric process. SVD handles any data transformation in 3 exact steps. First, it does a basis change. Basically, it rotates the original space to get the data perfectly aligned. Second, it scales those new coordinates using characteristic numbers called singular values, which are essentially the cousins of eigenvalues. And third, it does one final rotation to map the data right into its destination. That's the whole shebang: rotation, scaling, rotation. At the end of the day, that's really all any complex linear mapping is.
Now, what's really interesting about this is how perfectly visual it is. Imagine starting with just a basic plain square grid of vectors. The first part of the SVD grabs them and rotates them. Then, the singular value matrix stretches them out, embedding them up into a 3-dimensional space. And finally, there's one last rotation inside that new 3D space to lock it all in. SVD literally takes a messy, abstract grid and runs it through crisp, clean, distinct geometric steps.
Finally, step 5, decoding movie ratings data.
All right, we've covered a lot of beautiful, abstract math. But what does this actually look like in the real world? How does a computer use all this to understand us? Let's bring this completely down to earth. Imagine a super simple setup: 3 viewers, Ali, Beatrix, and Chandra, and 4 movies: Star Wars, Blade Runner, Amelie, and Delicatessen. They've rated these movies on a scale of 0 to 5. To the naked eye, this is just a random grid of numbers, pure chaos. But remember, SVD can factorize this non-square matrix to extract the underlying prime factors of these viewers' actual personalities.
When we run that ratings table through an SVD, we don't just get numbers back, we get incredible insights. SVD acts like a magic lens. If we only look at the most significant singular value, what we call a rank 1 approximation, the math automatically links Ali and Beatrix strongly with Star Wars and Blade Runner. Without us ever telling it what a genre is, the algorithm mathematically uncovers a hidden sci-fi lovers feature. If we fold in the second largest singular value, a rank 2 approximation, it suddenly isolates Chandra's strong connection to Amelie and Delicatessen. Boom, it just uncovered a French art house feature.
So the absolutely crucial point here is this: we never programmed the computer to know what movies were alike. We just applied SVD to factorize the data. By combining those rank 1 and rank 2 approximations, those isolated behavioral features, we can reconstruct the core patterns of the whole original dataset. We just throw out the tiny, noisy singular values. This dramatically compresses the massive data while perfectly retaining the actual human behavior inside it. And that, my friends, is the big picture. This isn't just about solving fancy equations on a chalkboard. By using matrix decompositions to summarize data into canonical forms, we are doing powerful dimensionality reduction. We're doing massive data compression. We are uncovering hidden heterogeneity, finding distinct little tribes like the sci-fi fans versus the art house fans, all from raw, unstructured grids of numbers. This math is the actual engine under the hood, powering the recommendation algorithms you interact with every single day.
Which leaves us with a kind of wild, fascinating thought to end on. Every time you stream a show, click to buy a product, or loop a song, you are adding numbers to a giant matrix out there. So, you gotta ask yourself, how much of your own daily digital footprint is being quietly factored, summarized, and understood as canonical forms by these exact SVD algorithms right this second? It's definitely something to think about the next time your favorite app recommends exactly what you were in the mood for. Thanks so much for hanging out with me on this explainer, and keep exploring the patterns hidden all around you.